150 million years ago. The Jurassic period. Dinosaurs dominated terrestrial ecosystems across every continent. Pterosaurs ruled the skies. And in the undergrowth, beneath the ferns and cycads, something extraordinary was happening. A lineage of small winged insects was losing its wings. Not through catastrophe or injury, but through evolution, through the slow, inexorable process of natural selection favoring a radical redesign. These insects were the ancestors of modern fleas, and they were about to undergo one of the most consequential evolutionary transformations in the history of life on Earth. They were trading flight for something else. Something that would, 150 million years later, facilitate the deaths of 200 million humans. They were evolving the ability to jump. The ancestral fleas were winged insects, probably similar to modern scorpion flies, with membranous wings and relatively normal insect proportions. They lived as ectoparasites, feeding on the blood of early mammals and possibly dinosaurs, though this remains debated among paleontologists. Fossilized fleas from the Middle Jurassic and early Cretaceous show intermediate forms, insects with reduced wings, enlarged hind legs, and specialized mouthparts for piercing skin and drawing blood. These fossils capture evolution in action, documenting the transition from flying blood feeders to jumping blood feeders. But why would an insect abandon flight, one of the most successful evolutionary innovations in the history of life? Why trade the ability to soar through three-dimensional space for the ability to leap in 2 dimensions? The answer lies in the specific ecological niche fleas were exploiting, the bodies of warm-blooded animals. Early mammals were small, often furry, and lived in burrows or dense vegetation. A flying insect trying to land on a fast-moving mammal covered in fur faced serious challenges. Flight requires space to maneuver. It requires visibility. It generates vibrations and sound that alert potential hosts. And once on a host, wings become liabilities, catching on fur, impeding movement through dense hair, making the insect conspicuous and easy for the host to remove through grooming. Natural selection began favoring individuals with reduced wings and enhanced jumping ability. Jumping offered precision. A jumping insect could launch itself from the ground or vegetation directly onto a passing mammal with explosive force. Jumping was silent. A jump generated no wing buzz to alert the host. Jumping was compact. A wingless body could slip through fur without obstruction, allowing the insect to hide deep in the host's coat where grooming could not reach. And so, over millions of years, wings shrank and disappeared while hind legs enlarged and transformed. The transformation of the hind legs was not simple enlargement. It was a complete biomechanical revolution, the development of one of the most sophisticated propulsion systems in the animal kingdom. Modern fleas possess hind legs that are approximately twice as long as their front and middle legs, creating an instantly recognizable profile. But the length is only part of the story. Inside those hind legs, fleas evolved a catapult mechanism based on elastic energy storage that allows them to achieve accelerations exceeding 100 times the force of gravity and reach velocities of 1.9 meters per second, extraordinarily fast for an insect measuring less than 3 millimeters in length. To put this in perspective, if a human being possessed equivalent jumping ability scaled to body size, that human could leap vertically 300 meters into the air, roughly the height of the Eiffel Tower, and cover 450 meters horizontally in a single bound. The flea jump is not merely impressive. It is a physical marvel that operates at the limits of what biological materials can achieve. The key to this extraordinary performance is a protein called resilin, one of the most remarkable biological materials ever evolved. Resilin is an elastomeric protein, similar in function to rubber but superior in almost every measurable property. It can be compressed to half its original size and will rebound with 97% efficiency, losing only 3% of the stored energy to heat. Synthetic rubbers typically lose 30 to 50% of stored energy with each compression cycle. Resilin can undergo hundreds of millions of compression rebound cycles without degrading, giving it effectively unlimited fatigue life under normal biological conditions. Synthetic rubbers degrade rapidly under repeated stress. Resilin functions across a wide temperature range, maintaining its elastic properties from near freezing to well above body temperature. Synthetic rubbers become brittle in cold or soft in heat. Resilin is, in engineering terms, nearly perfect elastic material, and fleas use it as the core of their jumping mechanism. The flea's jumping apparatus works like a miniature crossbow. Large muscles in the thorax contract slowly, compressing pads of resilin located in the flea's body. This compression stores elastic energy, just as drawing back a crossbow string stores energy in the bow's limbs. But the flea cannot release this energy immediately because the muscles are not strong enough to extend the legs at the speed required for jumping. Instead, the flea employs a catch mechanism, a biological latch that holds the legs in a cocked position while the muscles continue compressing the resulin. The catch mechanism is ingenious. The tendon of the primary jumping muscle passes slightly behind the coxotrochanter joint, the joint where the leg attaches to the body. This creates a torque that holds the joint closed with the leg folded tight against the body, like a locked hinge. The flea can maintain this position indefinitely, storing energy in compressed resulin while waiting for the right moment to jump. When the flea is ready to jump, a small trigger muscle pulls the tendon forward until it passes the joint axis. The torque reverses instantly. The catch releases, and the compressed resulin rebounds explosively, extending the leg and launching the flea into the air in less than 1 millisecond. The speed of this movement is almost incomprehensible. High-speed video recordings capturing 10,000 frames per second show the flea's leg extending from fully compressed to fully extended in approximately 1 millisecond. The flea accelerates at over 100 g, 100 times the force of gravity, achieving takeoff velocity in a time span too short for the human eye to perceive as anything but a blur. The acceleration is so extreme that it exceeds what muscle tissue can possibly generate through direct contraction. Muscle can contract at speeds of perhaps 10 times per second at maximum. The flea's jump requires acceleration 100 times faster. Only elastic recoil can generate such explosive movement, and only a material as perfect as resulin can store and release the necessary energy without failing. The flea has evolved a biological catapult that translates slow muscle work into explosive kinetic energy, solving the fundamental problem of how a tiny insect can generate enough force to launch itself dozens of times its own body length. But here is where evolution's cruel efficiency reveals itself. The jump was not evolved to spread disease. The jump evolved to allow fleas to colonize hosts efficiently. A flea in leaf litter or soil cannot fly to find a host. It must wait for a host to pass nearby and then launch itself with precision and speed before the opportunity disappears. The jump solved this problem perfectly. A flea can detect a potential host through vibrations, air currents, and chemical signals. When a mammal approaches, the flea orients toward it, cocks its legs, and waits. When the host is within range, typically a few centimeters, the flea jumps. The explosive acceleration allows the flea to close the distance in milliseconds, too fast for the host to react or evade. The flea embeds itself in the host's fur and begins feeding. Mission accomplished. The jump enabled fleas to become extraordinarily successful ectoparasites, colonizing mammals and birds across the planet, diversifying into over 2,500 species, each adapted to specific hosts. But the jump had an unintended consequence, a side effect that evolution could not have predicted because evolution does not predict. Evolution only selects for immediate reproductive success, not for long-term ecological consequences. The jump made fleas mobile. The jump allowed fleas to move between hosts. And that mobility, that ability to jump from a dying host to a living host, transformed fleas from mere parasites into vectors of apocalyptic disease. A flea that fed exclusively on one host for its entire life would not be a disease vector. It would be merely an irritation, drinking blood but not spreading pathogens beyond the individual it inhabited. But fleas do not stay on one host. They jump between hosts routinely, seeking better feeding opportunities, escaping grooming, fleeing dying or dead hosts. And every jump is a potential disease transmission event. The specific species that would become the primary vector of plague, Xenicilla chiopes, the oriental rat flea, evolved this host-switching behavior to an extreme degree. Xenicilla chiopes is not particularly host-specific. While it prefers rats, particularly black rats and brown rats, it will readily feed on humans, cats, dogs, and numerous other mammals when rats are unavailable. This lack of host specificity is unusual among fleas. Many flea species are highly host-specific, feeding almost exclusively on one species of mammal or bird. But Xenicilla chiopes is an opportunist, a generalist, willing to jump onto any warm-blooded animal that presents itself. And this flexibility, this willingness to switch hosts, made it the perfect plague vector. When rats died from plague, their fleas did not die with them. The fleas jumped to new hosts. And if those new hosts were humans, plague spread from the rodent reservoir into human populations. But even the jump alone was not sufficient to create a pandemic. Fleas had been jumping between hosts for 150 million years without causing plague pandemics. Something else was required. That something was Yersinia pestis, the plague bacterium, and specifically, a peculiar interaction between Yersinia pestis and the flea's digestive system. Yersinia pestis does something almost unprecedented in microbiology. It hijacks the flea's feeding behavior by physically blocking the flea's digestive tract. When a flea feeds on a plague-infected host, it ingests blood containing Yersinia pestis bacteria. The bacteria travel down the flea's esophagus into a structure called the proventriculus, a valve between the esophagus and the midgut that regulates blood flow into the digestive system. In a normal flea feeding on uninfected blood, the proventriculus opens, blood passes into the midgut, and digestion proceeds normally. But in a flea that has ingested plague bacteria, something different happens. Yersinia pestis multiplies rapidly in the proventriculus, forming a dense biofilm. The bacteria produce a sticky polysaccharide matrix that allows them to adhere to the walls of the proventriculus and to each other, creating a solid mass. This mass grows over several days until it completely blocks the proventriculus, preventing blood from passing into the midgut. The flea becomes blocked, a technical term for a flea whose digestive tract is obstructed by bacterial growth. A blocked flea is starving. It has a stomach full of blood trapped in its esophagus, unable to reach the digestive system. The flea becomes desperate, driven by hunger to feed more frequently and more aggressively than normal. But every time a blocked flea attempts to feed, it cannot swallow the blood it draws. Instead, it regurgitates the blocked mass of bacteria back into the bite wound. The flea becomes a biological hypodermic needle, injecting plague bacteria directly into every host it attempts to feed on. And because blocked fleas are starving and desperate, they bite repeatedly, moving from host to host, spreading plague with every attempted feeding. This is the biological accident that killed millions. The jump gave fleas mobility. The lack of host specificity gave Xenocilla chiopes the ability to move between rats and humans. And the proventriculus blocking behavior turned infected fleas into transmission machines that could not help but spread plague. None of these traits evolved to spread disease. The jump evolved to colonize hosts. The host flexibility evolved to maximize feeding opportunities. The proventriculus evolved to regulate digestion. But when these three traits combined with Yersinia pestis, they created a transmission system of terrifying efficiency. A single blocked flea could infect dozens of hosts before dying of starvation. A rat colony with hundreds or thousands of blocked fleas could seed a plague outbreak that would spread across continents. The jump that evolved to help fleas survive became the mechanism by which fleas spread death. The historical record documents this with brutal clarity. The Black Death, the Second Pandemic, the Great Pestilence of the 14th century, call it what you will, killed 75 to 200 million people between 1347 and 1353, roughly 30 to 60% of Europe's population and significant portions of Asian and Middle Eastern populations. The Third Pandemic, beginning in the 1890s in China, spread globally via steamship trade routes, killing approximately 12 million people in China and India alone before antibiotics finally brought it under control in the mid-20th century. And behind every death, behind every plague outbreak, was a flea. Not a rat, not contaminated air, not divine punishment, but a flea. A jumping insect measuring 2 millimeters in length, carrying a cargo of bacteria, moving from host to host with explosive leaps powered by compressed resolin. Consider the mathematics of plague transmission. A single infected rat can host dozens of fleas. When that rat dies from plague, all of its fleas must find new hosts within days or starve. A typical rat in a medieval city might carry 50 fleas. If half of those fleas are blocked with plague bacteria, that is 25 transmission-ready vectors jumping desperately toward any warm body within range. If humans are nearby, and in medieval cities, humans lived in extraordinarily close proximity to rats, those fleas will jump onto humans. Each flea will attempt to feed multiple times, injecting plague bacteria with each bite. Each human bitten has roughly a 60% chance of dying from bubonic plague without treatment, and a near certain chance of dying from septicemic or pneumonic plague if bacteria reach the bloodstream or lungs. Each dead human can seed new infections in anyone who handles the corpse or who is bitten by the fleas that abandon the cooling body. The transmission dynamics create exponential growth, classic epidemic curves that rise from a handful of cases to thousands within weeks. The jump made all of this possible. Without jumping ability, fleas would be like lice, insects that live on a single host for their entire lives, transferring to new hosts only through direct contact between host animals. Lice are not effective disease vectors for this reason. They cannot easily move between hosts that do not make direct physical contact. They cannot colonize new hosts rapidly. They cannot flee dying hosts. But fleas can do all of these things because they can jump. The jump gave fleas the mobility to be vectors. And once that mobility existed, plague exploitation was inevitable. Yersinia pestis did not need to evolve a complex transmission mechanism. It simply needed to exploit the mechanism that already existed, the jump that fleas had evolved for entirely different reasons. This is a crucial point that deserves emphasis. Evolutionary adaptations do not exist in isolation. They exist in ecological contexts, interacting with other species, creating opportunities and vulnerabilities that evolution could not foresee. The flea evolved jumping for host colonization in the Jurassic, 150 million years ago. Yersinia pestis evolved as a rodent pathogen probably less than 50,000 years ago, possibly as recently as 20,000 years ago. The two species were separated by 150 million years of evolutionary history, evolved on different continents in different ecosystems for different purposes. But when they came together, when Yersinia pestis infected a flea that possessed jumping ability and host-switching behavior, the combination created one of the deadliest disease transmission systems in history. This is the biological accident the title references. Not an accident in the sense of randomness, but an accident in the sense of unintended consequence, of convergence between traits that had no evolutionary relationship but whose combination produced catastrophic results for humans. Now consider the counterfactual. Imagine an alternate evolutionary history where fleas never lost their wings, never evolved jumping ability. In this alternate history, fleas remain flying insects, landing on hosts like mosquitoes, feeding briefly, and departing. These hypothetical flying fleas would not be effective plague vectors. A flying flea has no reason to stay on a dying host. It can simply fly to a new host, abandoning the dying animal long before plague bacteria build up to infectious levels. A flying flea has no particular incentive to bite repeatedly in the aggressive feeding pattern that characterizes blocked fleas. It can feed once, fly away, digest, and return days later for another meal. A flying flea would probably not spend enough time on any single host to ingest sufficient plague bacteria to become blocked in the first place. The flight-enabled escape behavior would break the transmission chain before it could form. Plague might still exist as a rodent disease, circulating in wild populations, occasionally infecting humans who handled infected animals. But without jumping fleas to vector plague from rats to humans efficiently, plague pandemics on the scale of the Black Death would be impossible. The jump made plague pandemics possible. The evolutionary loss of flight and gain of jumping was the accident that created the conditions for millions of human deaths. But evolution is not finished. Fleas continue to evolve, adapting to human countermeasures, developing resistance to insecticides, fine-tuning their jumping mechanisms for maximum efficiency. In Madagascar, where plague remains endemic and kills hundreds of people in bad years, studies of Xenocilla chiopes populations reveal widespread insecticide resistance. Fleas exposed to synthetic pyrethroids, the primary class of insecticides used for flea control, show knockdown resistance mutations in their voltage-gated sodium channels, the same resistance mechanism that makes mosquitoes resistant to pyrethroids. Over 70% of Xenocilla chiopes populations in some regions of Madagascar carry these resistance alleles, rendering pyrethroid insecticides increasingly ineffective. This is evolution in real time, selection pressure applied by human insecticide use driving genetic changes that allow fleas to survive treatments that would have killed their ancestors. And the jumping mechanism itself continues to be refined by selection. Recent research using high-speed video and biomechanical modeling reveals variation in jumping performance among flea species, with each species optimized for its primary host's behavior and habitat. Cat fleas jump differently than rat fleas, which jump differently than bird fleas. The angle of takeoff, the acceleration profile, the total distance covered, all vary based on the specific challenges each flea faces in colonizing its preferred host. Rat fleas, for instance, show trajectories optimized for jumping from ground level onto low-moving targets, exactly the geometry required to colonize rats moving along walls and floors. Human fleas, which parasitize humans less commonly now than in historical periods, show trajectories optimized for reaching heights of 50 to 70 centimeters, roughly ankle to knee height where they would contact human legs. The jump is not generic. It is tuned, precisely calibrated by millions of years of selection, to solve specific ecological problems. The resilin that powers these jumps is itself under active study by materials scientists hoping to synthesize it for industrial applications. Natural resilin outperforms any synthetic rubber in elasticity, durability, and energy efficiency. If we could manufacture resilin at scale, it could revolutionize applications from medical devices to aerospace engineering. But despite decades of research, we still cannot synthesize resilin that matches the properties of the natural material. Fleas produce resilin by expressing a specific protein, proresilin, which is then cross-linked through enzyme action to form the final elastic polymer. Researchers have successfully expressed proresilin in bacteria and achieved cross-linking, but the resulting material lacks the mechanical properties of flea resilin. Something about the natural production process, the precise molecular structure, the interaction with chitin in the insect cuticle, the specific cross-linking chemistry, produces properties we cannot yet replicate. The flea, an insect measuring 2 millimeters that most humans regard as a pest, possesses materials engineering capabilities we cannot match with all our modern technology. This raises uncomfortable questions about our relationship with fleas and our ability to control them. We have been fighting fleas for thousands of years. Ancient Egyptians used plant extracts and oils to repel fleas. Medieval Europeans scattered flea-bane herbs in their homes hoping to drive fleas away. Victorian pest control employed arsenic-based powders. Modern pest control uses synthetic pyrethroids, neonicotinoids, and insect growth regulators. And yet fleas persist. Global flea populations are not decreasing. If anything, they may be increasing as climate change expands the geographic range of flea-suitable habitats and as urbanization creates more edges where wild and domestic animals interact, facilitating flea transfer between species. We have not won the war against fleas. We have merely forced them to evolve resistance to our weapons. And plague remains. The World Health Organization reports 2,000 to 3,000 plague cases annually, with most occurring in Madagascar, the Democratic Republic of Congo, and Peru. These are confirmed cases. Actual numbers are likely higher, perhaps double or triple the reported figures, as many cases occur in rural areas with limited medical infrastructure and never get officially diagnosed. Plague kills approximately 600 people per year globally based on reported data. 600 deaths may seem small compared to the millions killed by malaria, tuberculosis, or HIV. But plague is treatable. Those 600 deaths are preventable deaths, occurring because patients do not receive antibiotics in time, or because medical facilities lack diagnostic capabilities, or because patients live too far from clinics to reach treatment before the disease progresses beyond saving. Every plague death in the modern era represents a failure of public health infrastructure. More concerning is the ever-present possibility of antibiotic-resistant plague. Yersinia pestis remains largely susceptible to antibiotics. Streptomycin, gentamicin, doxycycline, and ciprofloxacin all work effectively if administered early enough. But antibiotic resistance genes spread readily between bacteria through horizontal gene transfer, bacteria sharing genetic material across species boundaries through plasmids and other mechanisms. Resistance genes for all major antibiotic classes have been found in environmental bacteria living in the same habitats as Yersinia pestis. It is not a question of whether resistance can evolve. It is a question of when and what we will do if it does. An antibiotic-resistant strain of Yersinia pestis would return us to medieval vulnerability. 60% of infected people would die without treatment. And if that resistant strain emerged in an area with high flea populations and poor public health infrastructure, it could spread before we realized what was happening. The fleas would still be there, jumping, transmitting, spreading disease with their 150-million-year-old mechanism that humans have never successfully countered. We can kill fleas individually. We can reduce flea populations temporarily. We can treat plague with antibiotics as long as resistance does not emerge. But we cannot eliminate the jump. We cannot unevolve the trait that makes fleas effective vectors. The jump is written into flea biology at the deepest levels, encoded in the genes that build resilin, in the developmental programs that construct the hind legs, in the neural circuits that coordinate the trigger mechanism. As long as fleas exist, the jump exists. And as long as the jump exists, Fleas will be capable of vectoring disease between hosts. This brings us to a crucial realization about evolution and disease. Evolution does not care about human welfare. Evolution is not designing organisms for our benefit or detriment. Evolution is simply the process of differential reproductive success, of traits that help organisms survive and reproduce becoming more common over generations. The flea's jump is an exquisite adaptation for a specific ecological function. It is a masterpiece of biomechanical engineering, a solution to the problem of how a wingless insect can colonize mobile hosts. The fact that this solution also happens to make fleas efficient disease vectors is, from evolution's perspective, completely irrelevant. Evolution does not foresee consequences. It only selects for immediate reproductive fitness. And from the flea's perspective, carrying plague is probably neutral or even slightly negative. A flea blocked with plague bacteria is a starving flea that will die within days or weeks. Plague infection shortens flea lifespan and may reduce reproductive success. Fleas do not benefit from carrying plague. They are manipulated by bacteria that hijack their feeding behavior for bacterial transmission. The flea is as much a victim of Yersinia pestis as humans are, just in a different way. The bacteria exploits the flea's jumping ability and feeding behavior for its own reproductive success, using the flea as a vehicle to move between mammalian hosts where the bacteria can multiply. This is the dark reality of disease ecology. Pathogens evolve to exploit whatever transmission opportunities exist in their environments. If a vector exists with the right biology, the right behaviors, the right population density, pathogens will find ways to exploit that vector. Fleas possess the right biology, jumping ability, host-switching behavior, blood feeding with potential for regurgitation. Fleas exist in high densities wherever rodents live near humans. Fleas provide a transmission opportunity, and Yersinia pestis evolved to exploit that opportunity with ruthless efficiency. The result is plague, one of the deadliest diseases in human history, enabled by the jump, by a trait that evolved 150 million years before humans existed. The lesson here is about unintended consequences on evolutionary timescales. When fleas lost their wings and gained jumping ability in the Jurassic, mammals were small shrew-like animals and humans would not exist for another 150 million years. The evolutionary pressures shaping flea anatomy had nothing to do with human disease. They had to do with host colonization efficiency in Jurassic and Cretaceous ecosystems. But the traits that emerged from those ancient selection pressures became, 150 million years later, the mechanisms of plague transmission that killed 200 million humans. This is not foresight. This is not design. This is contingency, the idea that historical accidents shape future possibilities in ways that could never be predicted. If we could rewind evolutionary history and replay it, would fleas evolve jumping again? Maybe. The ecological pressures favoring jumping were strong, and the solution, elastic energy storage in resilin, is elegant enough that convergent evolution might produce it repeatedly. But maybe not. Maybe in a replayed history, fleas would evolve a different solution to the host colonization problem, perhaps enhanced gripping ability allowing them to cling to hosts while retaining flight, or perhaps chemical camouflage making them undetectable to host grooming behaviors. In that alternate history, fleas might still be parasites, but they would not be plague vectors, and the Black Death might never have occurred. History is contingent on the specific evolutionary paths that happen to be taken, paths that could have gone differently. But in our history, in the actual timeline we inhabit, fleas evolved jumping. And that jump killed millions. The oriental rat flea, Xenocyliciopes, carrying its cargo of Yersinia pestis, jumping from dead rats to living humans with explosive leaps powered by compressed resilin, spread plague across 3 continents and destroyed civilizations. The fall of the Roman Empire in the 6th century may have been accelerated by the plague of Justinian, a plague pandemic that killed perhaps 50 million people and destabilized the empire economically and militarily. The Black Death of the 14th century killed perhaps half of Europe's population and transformed European society, ending feudalism, empowering labor, inspiring the Renaissance, and indirectly contributing to the Protestant Reformation through the crisis of faith it generated. The third pandemic of the late 19th and early 20th centuries spread plague to every inhabited continent except Australia, killed millions, and drove the development of modern epidemiology and public health infrastructure as societies struggled to understand and control the disease. All of the death, the social transformation, the scientific progress forced by catastrophe, traces back to the jump. to a biomechanical innovation that evolved 150 million years ago for reasons having nothing to do with human disease, to resilin compressed and released in less than 1 millisecond, to fleas launching themselves from dying hosts to living hosts, from rats to humans, carrying bacteria in their blocked proventriculus, unable to feed, unable to digest, driven by starvation to bite repeatedly, spreading plague with every desperate attempt to draw blood. The flea does not know it is a disease vector. The flea is simply trying to survive, following behavioral programs written by evolution over millions of years. Feed, jump, find a host, feed again. These simple imperatives, executed by an insect with a brain smaller than a grain of sand, produced consequences that reshaped human civilization. This is the terrible power of biology, the way simple mechanisms operating at small scales can cascade into consequences at civilizational scales when conditions align in the right ways. And those conditions persist. Fleas still jump. Rats still carry fleas. Yersinia pestis still circulates in rodent populations on every inhabited continent except Australia. Humans still live in cities where rats thrive. The transmission chain remains intact, broken only temporarily by antibiotics and public health measures that require constant effort and resources to maintain. If those measures falter, if antibiotics fail, if public health systems collapse under the weight of multiple simultaneous crises, plague will return. And it will spread the same way it has always spread, flea by flea, jump by jump, host by host. This is not alarmism. This is recognition of biological reality. We have not eliminated the mechanisms that make plague transmission possible. We have only suppressed the disease through medical interventions. The difference is crucial. Elimination means the threat is gone. Suppression means the threat is controlled but persistent, ready to resurge if control measures fail. Plague is suppressed, not eliminated. And the suppression depends entirely on systems that are fragile, underfunded, and vulnerable to disruption. Consider what would happen in a major civilizational disruption. War, economic collapse, climate catastrophe, or even another pandemic could overwhelm medical systems and public health infrastructure. Antibiotic production could be disrupted. Hospitals could be overwhelmed. Flea control programs could be abandoned as resources flow to more immediate crises. Rat populations could explode as sanitation systems fail and garbage accumulates. And plague could reemerge, spreading through crowded cities where rats and humans live in close proximity, transmitted by fleas jumping from host to host with the same explosive efficiency that killed millions in medieval times. The jump would still work. Resilin would still compress and rebound with 97% efficiency. Fleas would still launch themselves at 100g acceleration toward any warm-blooded animal within range. The mechanism is timeless, unchanged by human technology or social progress. We exist in a temporary window where antibiotics work and public health systems function well enough to suppress plague. But that window could close. And if it does, we will rediscover what medieval people knew viscerally. That tiny jumping insects can bring death, that biological mechanisms evolved for entirely different purposes can become instruments of apocalypse when exploited by the right pathogen at the right time. So the flea jumps. It has jumped for 150 million years, and it will jump for another 150 million years if fleas survive that long. The jump that evolved to colonize Jurassic mammals became the jump that spread plague across medieval Europe, became the jump that persists today in every flea on every rat in every city worldwide. Evolution built the jump for one purpose, and plague hijacked it for another. The biological accident was the convergence of these two things, the ancient adaptation and the modern pathogen, creating a transmission system of terrible efficiency. We cannot undo evolution. We cannot make fleas unevolve their jumping ability. We can only work with the biology we have inherited from deep time, managing threats, suppressing diseases, maintaining vigilance. The flea learned to jump 150 million years ago. That lesson killed millions. And the flea has not forgotten. It jumps still in your home, in your city, on rats living in walls and sewers, carrying the possibility of plague in its blocked proventriculus, ready to spread death again if we ever lower our guard. This is the legacy of evolutionary contingency, of ancient adaptations producing modern consequences, of biology operating according to its own logic without regard for human welfare. The jump continues. The threat persists. And we remain, as we have always been, vulnerable to biological accidents that occurred long before we existed and will continue long after we are gone.